Greetings, everybody. Learning is a hobby here. In this video, I want to do my summary for Chapter 1 in Michael O. Searcoid's Metric Spaces. Generally, when I start a new book, I like to, read the introduction, the author's introduction, but I'm kind of in a rush today, so I'm going to do that in another video. So this video here is just going to be my summary for Chapter 1. I haven't even started on the exercises yet, but as always, let me know what you think down below. Um, this book is put out by Springer, by the way. It's an undergraduate book. Um, I would suggest before you start this, at least having a course in a proof-based course in linear algebra and also in analysis. Maybe some topology if you have time for that, but definitely analysis and linear algebra would help with understanding this stuff in this book. So let me go through my summary for chapter 1. Like I said, I'm kind of in a rush today, so I'm just going to get right to it. Um, okay, so let's see. Let me just rearrange my screen here. Okay, so this is I had to break this up into two sets of lecture notes because I usually uh, make 20 pages and then I upload it as a PDF and then I just write on it like that. Um, and I ran out of the 20 pages, so I had to start a new set of lecture notes. So there's two set of lecture notes on the Patreon page if you're looking to look at these notes yourself. So okay, let's start with at the beginning. So metrics. This book is about functions that measure distance. Prototype for distance is the Euclidean distance between points in the plane, which you should be familiar with before you do this book. In the context of metric spaces, by distance we mean a kind of difference between distinct points. Distance is not always measured in straight lines. We often find ourselves in situations where units of length also are not the most informative for measuring distance. For example, we may prefer a measure of the time it takes light to travel between the 2 points. Let's examine the fundamental properties of our prototype, which is the Euclidean distance between 2 points in the plane. All right, the Euclidean distance deals with a well-defined set of objects, which are points in the plane. It measures the distance between pairs of distinct objects in this set using positive real numbers and measures as zero the distance between each point and itself. It has symmetry, meaning the distance from A to B is the same as the distance from B to A. And 4, the line segment between 2 points provides the shortest way possible between them. No legitimate route that passes through a third point is shorter. All right, so that brings us to section 1.1, and we begin with the definition of a metric. Suppose X is a set and D a real function defined on the Cartesian product, X times X. Then D is called a metric on X if and only if for each A, B, C in X. Then we have these three properties. The first is called the positive property. D of AB is greater than or equal to 0, and D of AB is 0 if and only if A is equal to B. Then we have second, the symmetric property. D of AB is the same as D of BA. And finally, the triangle inequality. D of AB is less than or equal to D of AC plus D of CB. So we're sort of mirroring the important properties of the Euclidean metric here to generalize. Right, the set X endowed with the metric D is called a metric space, and for A, B, and X, D of AB is the distance between A and B with respect to the metric D. If there's any ambiguity as to which metric is being used, we specify it explicitly with the notation in parentheses X comma D. Right, then we get our first theorem, theorem 1.1.2, which is a rearrangement of the triangle inequality. We've seen this already in Spivak, but the triangle inequality is really important in this subject. So suppose X is a metric space and A, B, and C are in X, then the absolute value of D of AB minus D of BC is less than or equal to D of AC. So it's just a restatement of the triangle inequality. All right, and here's the proof. let A be C in X by the triangle inequality. We have these two inequalities, D of AB less than or equal to D of AC plus D of CB, which is the same thing by symmetry of equals DAC plus DBC, and also inequality number two, DBC less than or equal to DBA plus DAC equals DAB plus DAC. Um, then we can rearrange some things. So for example, in the first inequality, I can subtract um, uh, the distance between B and C from both sides, and that gives me the inequality that I have over here, and then subtract AB, just the distance between AB from the second inequality, and that gives us this one here. And notice that that's the same. If you take those two things together, it's the same thing as what we wanted to prove. Okay. Then there's a bunch of examples in this chapter, some of which are referred to, some of which are really standard, but some of which are referred to in the exercises. I didn't do all of the examples because, like I said, there's a lot of them here. I just did sort of the important ones and the ones that are referenced later on in the exercise set. So um, R, along with the absolute value function, is a metric space where the distance between the two real numbers A and B is the absolute value of A minus B. This is called a Euclidean metric on the real numbers. And unless stated otherwise, we'll assume that R is endowed with the Euclidean metric. The Euclidean metric on R is dependent not simply on the algebraic structure of R, but also on the total ordering of R. So for A, B, and R, the absolute value of A minus B is A minus B if B is less than or equal to A, and the absolute value of A minus B is B minus A. Otherwise, is B minus A otherwise. This relationship between metric and order has many repercussions. For example, the intuitive idea of betweenness in the ordering of R is captured by this particular metric of R. Specifically, if A, X, B are real numbers and either A less than equal X less than equal B, or B less than or equal X less than or equal to A, then X lies between A and B. Once the metric is defined, the same thing can be said in a different but more obscure way, which is X lies between A and B if and only if the absolute value of A minus B is equal to A minus X, the absolute value of A minus X plus the absolute value of X minus B. Right, next example, if D is the empty function, then the empty set along with that metric is a metric space, although not a very interesting one. Also, if we have the function D from the singleton set containing A to the singleton set containing 0, then the metric space containing the singleton set A along with the metric D is a metric space. Right, example 115, if D is a function from the Cartesian product of the complex numbers with itself to the interval from 0 to infinity, where the distance between Z and W is given by the modulus of Z minus W, then we get a metric space. This is the usual metric defined on C. We will assume C is endowed with this metric unless otherwise stated. All right, here's one that is not, that you haven't seen before, maybe. Suppose C is a circle, and for each A, B, and C, define the distance between A and B to be the distance along the line segment from A to B, then C comma D is a metric space. So here we're taking the distance between A and B on the circle here to be the length of the line segment connecting these 2 points on the circle. Note the fact that the route from A to B goes outside C is irrelevant. A metric does not take into account any route traveled from one point to another. In this respect, our R2 prototype displays more information than is used for the definition in general of a metric. Right, here's another example. Every set admits a metric. This is called a discrete metric. Let X be a set and D from X times X to the set containing just the 0 and 1, so it's a pair set, such that for X, Y, and X, the distance between X and Y is 1 if X is not Y and 0 if X is Y. Then XD is a metric space. Here's a note. If the absolute value X if the cardinality of X is greater than 1, then for any lambda in 0 to infinity and D a metric on X, lambda D is also a metric on X. Also, if D is a metric on X, so is the function E, which is defined to be D over 1 plus D, so that for any AB in X, E of AB is equal to D of AB over 1 plus D of AB. And note that the range of E is the interval from 0 to 1, irrespective of the values of D. Right, then he intersperses questions at the end of each section here as well. So question 111 says this. Ask question one. Oh, I'm sorry. This is referring to an exercise set. Sorry. Question 111 asks the reader to verify that E is a metric on X. To this end, the reader should, he just gives a hint here. To this end, the reader should check that for X, Y, Z in the positive real numbers, um, Z less than equal X plus Y implies the inequality here. So we'll do this when we get to the exercise set. Like I said, I haven't done that yet, but when we get around to the exercise set, that we'll use this hint, and I'll refer back to it to remind people that are watching the video. Here's example 118. By using the Pythagorean theorem twice, we arrive at the usual Euclidean metric on R3. Namely, if xy is in R3, then the distance between x and y is the what's the norm on x minus y? We haven't talked about norms yet in this book, but we actually talked about this if you go to my notes on uh, the book Multivariable Mathematics by Theodore Schifrin, we talked about this. We derived this formula. Okay, here's another example. Like I said, there's a lot of them here. Example 119, let C be a circle. And for any A, B, and C, define the distance from A to B, to be the shorter distance between the circle along the circle from A to B, then D is a metric on C. Similarly, if S is a sphere and AB are elements of S, or points on S, then we can define the distance from A to B to be the shortest distance along a great circle joining A and B. This is well defined and thus determines a metric on S because the great circle is unique unless A and B are equal or antipodal. All right, here's another standard example, 1110. The function taking the ordered pair A comma B to that sum defined on R to the n times R to the n is the usual Euclidean metric on Rn. We will always assume R to the n is equipped with this metric unless stated otherwise. The reader's asked to supply a proof of this metric, that this metric satisfies the triangle inequality, but we'll do that in the exercise set. In fact, I don't know if my memory is correct, but I think we might have shown that this satisfies the triangle inequality in Spivak or in Schifrin. If not, we'll do it again in the exercise set here anyway. But I feel like we already did that in one of the other books on the channel. But like I said, when we get to the exercise set, we'll do it again. Uh, we'll give a proof of a much more general result later in the book, which is in chapter 12. Okay, example 1111. There are many metrics on R itself. For example, any injective function f from R to R generates a metric. So the ordered pair, if we take the ordered pair AB to the absolute value of f of A minus f of B on R, that gives you a metric. A more general result holds for injective functions into any metric space, which we'll look at in question 112 in the exercise set. And just a note, injectivity is necessary to ensure that distinct points have non-zero distance. Symmetry is built into the definition, and the triangle inequality follows as a consequence of the fact that the absolute value satisfies the triangle inequality. So we already know that. Again, we did that in Spivak, and I think we even did it in Tau as well. All right, here's example 1112. Since the inverse function x to x inverse is injective, the function that takes the ordered pair AB to the absolute value of A inverse minus B inverse is a metric on the positive real numbers. And again, we'll look at this in the exercise set in question 112. This is called the inverse metric. A similar metric can be put on the natural numbers along if we union that with the singleton set containing infinity. So in other words, we treat the natural numbers along with we'll call it the point at infinity, by defining the ordered pair of natural numbers mn to take that to the absolute value of m inverse minus n inverse, and d of n infinity equals d of infinity n to be n inverse for all m, n, and n, and d infinity infinity will define to be zero. So again, we'll look at this more in question 114 in the exercise set. This is called the inverse metric on n squiggle or n tilde. All right, example 113, the function mu1 defined on Rn times Rn by uh, taking the the point in Rn a the points in Rn a comma b to the sum of the difference of the absolute value of the difference of their respective coordinates, and we sum them all up as a metric on Rn. If n is equal to 2, this is called a taxicab metric, and again we'll see that we'll prove that in that this is a metric, I guess, in question 1.5 in the exercise set. Just a side note, I have a whole book on the taxicab geometry, which I would like to do on the channel at some point. I don't know. Let me know what you guys think down below if you'd like to see that. It's a Dover book. It's a small little pamphlet, it'd be a nice little project book. Um, Okay, example 1114, the function mu infinity, which takes the points a comma b to the maximum of the absolute value of the distance of the coordinates um, for all I in n sub n. So here, this gives you the natural numbers up to the dimension of the space is a metric on Rn. Again, see question 1.5 in the exercise set. All right. Example 1.115, define D on R2 times R2 as follows. So the distance between A and B is 0 if A is equal to B. It's equal to the square root of B1 minus A1 squared plus B2 minus A2 squared. If A is not B and A not 0, or B is not 0, and it's equal to 1 plus the square root of the sum of the differences of the coordinates otherwise. Then D has the positive property and is symmetric. Moreover, D coincides with the Euclidean metric on R2, except when exactly one of A and B is the origin. For all A, B, C in R2, we have the distance between A and 0 less than or equal to the distance between AC and plus the distance between C 0, and the distance between A, B less than or equal to distance A comma 0 plus distance 0 comma B by the triangle inequality for the Euclidean metric on R2, so that D also satisfies the triangle inequality and is therefore a metric. All right, like I said, you're gonna have to bear with me. There's a lot of examples here. Example 1.116. This is an interesting metric. Eventually on the channel, I want to get to p-adic analysis, and this is the metric they use for that. Let P be a prime number. Any X in the rationals minus 0 can be expressed as P to the K times R over S for a unique value of K in Z, where R is an integer, S is an integer, and P does not divide R, P does not divide S. Then we define the metric of X, the p-adic metric of X to be P to the minus K if X is not 0 and 0 if X equals 0. The p-adic metric on Q is defined to be you take the two rational numbers A, B to the p-adic metric of A minus B. This is clearly non-negative and symmetric. The triangle inequality is easily verified using this property here, and I'm assuming that he asks us about this in the exercise set. But like I said, eventually on the channel, I want to do a whole series on p-adic analysis because if you've been watching for a while, I'm interested in number theory and so on. So okay, next one. Example 1.117, let f be the set of all functions from 0 to 1 to the closed interval from 0 to 1 to the closed interval from 0 to 1. For each fg and f, define S of fg to be the supremum of the set of all absolute values of differences of f of x minus g of x for all x in the closed interval from 0 to 1. Then S is a metric on f. And here's the proof. You just have to show that it satisfies the three conditions. Maybe just so that this doesn't go on too long, I'll just let you guys pause your screen if you want to see this. You just prove the three properties that show it's a metric. So here are the three things. Okay, example 1.118, let I be the set of all closed intervals from A to B which are intervals of the real numbers, where a is less than or equal to b. Let I be the interval from a to b and j the interval from r to s. Define the distance between I and j to be the maximum of the distance between the endpoints of the. I'm sorry, no, it's the max. Sorry, it's the maximum of the absolute value of r minus a, r minus a, or the distance or the absolute value between s minus b. Sorry, it's not the lengths of the intervals. Then D is a metric on I. And again, you can show that that's a metric by just showing that it satisfies the three properties for a metric. Again, I won't belabor this just because I don't want this video to be too long, but if you want to see my proof here, you can look at pause your screen and look at the proof. All right, just a note, we restricted I to intervals of the form AB to ensure that D is um, a real number. For example, we left out the intervals where one of the endpoints is infinite. We also left out, intervals that are not closed to ensure that dij is 0 implies that I is j. In section 7.3.1, we'll see that there are possibilities for extending this metric to an even larger collection of subsets of R than I. All right, example 119. There are familiar situations that are not encompassed by the theory of metrics. For example, many cities have one-way traffic systems. Here, the distance function may not be symmetric, even though it does satisfy the triangle inequality. So, not everything is a metric. All right, here's section 1.2, point functions and point-like functions. Let's start with the definition. 1.2.1, suppose xd is a metric space and z an element of x. We shall call the non-negative real function x to d of zx defined on x the point function at z and denote it by delta sub z. The set of all such functions that consists of all point functions on x will be denoted by delta of x. All right, theorem 122 then. Suppose xd is a metric space. The function z to delta z is a bijective function from x onto delta x. And you just have to show that it's injective and bijective. And again, we've done this a bunch of times, so I'm not going to belabor the proof here. You can pause your screen if you want to see my proof. Here's my proof that it's injective. Here's my proof that it's surjective. All right, example 1.2.3, let n be a natural number. In Rnd, where d is the Euclidean metric, we can recover the metric entirely by knowing delta sub 0 and using the equation dab equals delta sub 0 of b minus a. In fact, we can recover d from any delta sub z by using the formula dab equals delta sub z of z minus b plus a for all a, b, and Rn. This sort of thing is not possible, unfortunately, in an arbitrary metric space because we do not have the algebraic operations of addition and scalar multiplication in general. We can, however, recover the metric by knowing all or a good many of the point functions because delta sub b of a is equal to d of ab, which is also equal to delta sub a of b for all a, b, and x. Right here, next theorem, 1.2.4, suppose xd is a non-empty metric space and z an element of x, then there's two properties here. Delta sub z of b minus delta sub z of a is less than or equal to dab, less than or equal to d sub z of b plus d sub z of a for all a, b, and x, and also delta sub z of z is equal to 0. This just follows from the properties of metrics. So that's my proof here. Definition 1.2.5, suppose xd is a non-empty metric space and u a function from x to r plus. We shall call u a point-like function on x if and only if u of a minus u of b less than or equal to d of ab less than or equal to u of a plus u of b for all a, b, and x. In other words, if it satisfies the first condition in theorem 1.2.4. Right, so this is point-like, not a point function, right? These are point functions. Theorem 1.2.6, suppose xd is a metric space and u from x to r plus, then u an element of delta of x, if and only if u is a point-like function on x and u is an element of u of x. In that case, there's a unique w in x such that u is delta sub w. All right, I will go through this proof because this is important. it's a biconditional, so we have to do both directions. So first we'll start with letting u be an element of delta of x, then u is point-like, and 0 is an element of u of x by theorem 1.2.4. And then we do the reverse direction, let u be a point-like function on x and 0 be an element of u of x. Then there's b in x such that u of b equals 0. Then for any a in x, u of a is equal to u of a minus u of b, less than or equal to d of ab, less than or equal to u of a plus u of b, which is also u of a because u of b is 0, which implies that u of a equals d of ab, which is delta sub b of a. Lastly, b is unique by theorem 1.2.2. Remember, the point functions are bijective. Okay, section 1.3, metric spaces and metric subspaces. Each set X has a collection of subsets. Its power set P of X. We've talked about power sets in tau if you want to look more into that. Each metric defined on X not only makes X into a metric space, but determines a metric on each member of the power set of X. Okay, here's a definition, 1.3.1. Suppose XD and YE are metric spaces. We say that X is a metric subspace of Y, and Y is a metric superspace of X if and only if X is a subset of Y, and D is a restriction of E. And a note here, we will often, provided that it leads to no confusion, use the same letter to designate the metric on a subspace and the metric on a superspace. All right, here's some natural examples. R with its usual metric is a metric subspace of C, and so on and so on. You can look at this. I'm not going to go spend too much time on this example. These are examples you should be aware of. Question 1.3.3. If Y is a metric and X is a subset of Y, then X is made into a subspace of Y in one way only, by restricting the metric of Y to X times X, the Cartesian product. However, suppose XD is a non-empty metric and Y a proper superset of X. Is it always possible to define a metric on Y that is an extension of D? And in fact, there are many ways you can do it. Here's one way. Extend D to the set X times X union Y minus X times Y minus X by endowing Y minus X with any metric, labeling it D also, then fix 2 points, A and X, B and Y minus X. Then for each Y in Y minus X and X, set D of YX equal D of XY plus equals D of XA plus 1 plus DBY, thus extending D to Y times Y. And this D is a metric on Y. We'll prove that in the exercise set. All right, so that's interesting. We can always extend a metric space to a super set by using this process here. All right, section 1.4 deals with isometries. Despite the differences in the algebraic structure between C and R2, there's no detectable difference other than labeling between them when viewed simply as metric spaces. All right, and here's a definition. Let XD, YE be metric spaces and phi from X to Y. Then phi is called an isometry or an isometric map if and only if E of phi of A, comma phi of B is equal to D of AB for all A, B, and X. If phi is an isometry, we say that the metric subspace phi of X, comma E of Y, comma E is an isometric copy of the space X, comma D. It's kind of like an isomorphism, but for metrics. There's a proposition here that I guess we'll prove in the exercise set, so I didn't prove it here. Suppose XD and YE are metric spaces, and phi from X to Y is an isometry, then phi is necessarily injective, and we'll prove that in question 121 when we get to the exercise set. And its inverse, phi inverse from phi of X to X is also an isometry. Right. Here's a note. As metric spaces, X and phi of X are indistinguishable. Phi of X is simply a relabeling of X with phi of A in place of A for each A in X. Therefore, we will often suppress the function phi and treat them as if they are identical. Remember, however, that X and phi of X may have differing non-metric structure. For example, think about the complex numbers in R2. Okay, example 142, phi from R2 to C. where phi of AB is A plus IB is an isometry. Well, here's another example, 1.4.3. While R and R2 are not strictly speaking subspaces of R3, R is isometric to the set of A in R3, where A2 equals A3 equals 0. In other words, the x-axis in R3, and R2 is symmetric to the XY plane. Sorry, isometric to the XY plane in R3. Various other lines and planes in R3 are also isometric to R and R2, respectively. Okay, example 1.1.4. Suppose Z is a set, X comma D is a metric space, and f Z to X is an injective function, then F and D induce a metric on Z. So if you take the pair AB to D of F of A, comma F of B, we'll prove this in question 1.2. Then we get that induces a metric on the set Z. So this makes this is just what I said, but this makes Z isometric to the metric space F of Z comma D, which is a subset of the metric space X comma D, and F is an isometry. Okay, section 1.5, extending a metric. Theorem 1.5.1 is what we begin with. Suppose X comma D is a non-empty metric space and let X prime denote the set of all point-like functions on X. Define S on the Cartesian product of X prime with itself to be the function that takes U comma V to the supremum of the absolute value of U of X minus V of X for all X and X. Then S is a metric on X prime. Moreover, delta of X is a subset of X prime, and the map Z to delta Z from XD onto the subspace delta X comma S of X prime of S is an isometry. So delta of X comma S is an isometric copy of X comma D. And the proof just shows, first of all, that S is a metric. And like I said, I won't belabor this. You can look at my proof here if you want to by pausing the screen. You have to show that it has all the properties of being a metric, which is 1, 2, and 3. Or sorry, which one shows that it's a real valued function, sorry, and then 2, 3, and 4, and 5 show that it's a metric. So 5 is the triangle inequality. Therefore, S is a metric on X prime. Like I said, I won't go through that in detail. You could, again, if you don't want to pause your screen, just so you know, if you become a member on Patreon, you can download all of these lecture notes for free. Next, clearly, delta of X is a subset of X prime by theorem 1.2.4. Also, theorem 1.1.2 implies that delta sub P of A minus delta sub Y of A in absolute value is equal to D of PA minus D of AY, less than or equal to D of PY for all APY in X, and delta P of P and delta Y of P equals DPY equals absolute value delta sub P of Y minus delta sub Y of Y, which implies that S of delta P delta Y equals D of PY for all X. Sorry, for all PY and X, which implies that Z to delta Z is an isometry from XD to delta XS. So these are isometric copies of each other. All right, note, thus we have shown how to build a natural extension X prime of an arbitrary metric space X. Just as R2 and R3 are not strictly metric subspaces of R, but are thought of as such because they contain naturally occurring isometric copies of R, neither is our extension strictly a metric superspace of X, but it may be thought of as such because it includes a naturally occurring isometric copy of X. We shall make use of this later on in section 10, in chapter 10, rather. Okay, section 1.6, metrics on products. To start with a note here. There are many ways products of metric spaces can be endowed with a metric. There's no reason why an arbitrary metric on a product should bear any clear relationship to the metrics on the individual spaces, but we are particularly interested in those that do. For the moment, we'll fix our attention on what we shall call conserving metrics, which we'll define in 1.6.4 down below in a second. All right, but first, here's a theorem. Theorem 1.6.1. Suppose n is a natural number, and for each I in n sub n, xi comma tau I is a metric space, then the following three functions are metrics on the product space of the xi's. So mu1 is the metric that takes the ordered pair AB to the sum I going from 1 to n of tau of I of AI BI. U2 is defined in the way that you see here. I won't read it out. And mu infinity is defined to be the maximum of the tau I of AI BI for all I in n sub n. Moreover, for each AB in the product space, we have mu infinity of AB less than equal mu2 of AB less than or equal to mu1 of AB. All right, these are you might notice mu1 and mu2 are actually the analogs of the Euclidean metrics on R1 and R2 if tau I is the Euclidean metric on R. All right. The metric mu2 will be called the Euclidean product metric for reasons I just stated. So here's the proof that mu1, mu2, mu infinity are non-negative and symmetric, and that mu j a b equals 0 only when a equals b. For j equals 1 to infinity are clear, so I'll skip that. See, oh, actually, I guess we won't skip it. We'll do that in the exercise set in question 1.5 and 1.4 for the triangle inequality. 2, let tau j, aj, bj be the maximum of tau I of ai bi for all I in n sub n. Then mu infinity AB is equal to this value of the norm on xj. That's obviously equal to the square root of the square of that element because the norms are always non-negative, right? Sorry, the metrics, sorry, are always non-negative, which is less than or equal to the sum of the products. Sorry, the sum of the metrics on those coordinate values which is equal to mu2 of AB. So that shows the first inequality. Um, sorry, the second shows the second inequality. No, I'm sorry, the left-hand part. Let me go back up. That shows this part of the inequality. And then the second part of the inequality also follows from this fact here that if you square mu2 of AB, then that gives you this sum of squares here. And if you actually multiply out the square of mu1 of AB, you get this expression here, and that's clearly greater than mu2 of AB. Okay, here's definition 1.6.2. Suppose n is a natural number, and for each I in n sub n, xi tau I is a metric space. Suppose E is a metric on the product space of the xi's. We shall call E a conserving metric on the product with respect to the given metrics tau I, if and only if for all AB in the product space, we have this inequality here, mu infinity of AB less than or equal to EAB less than or equal to mu1 of AB. And we'll call E simply a conserving metric if the metrics tau I and xi are clear from the context. Here's an example. 1.6.3, mu1, mu2, mu infinity are themselves conserving metrics. The functions defined in 1.1.13, 1.1.14, and question 1.4 are the metrics mu1, mu infinity, and mu2 respectively on Rn. Mu2 is the usual Euclidean metric. We already mentioned this. So assuming each copy of R has its usual metric, the Euclidean metric on Rn is conserving. The metric on R2 and 1.1.15 is not conserving, and I guess we'll look at that in the exercise set in question 120. All right, what do conserving metrics conserve? If n is a natural number, and for each I in n sub n, xi tau I is a non-empty metric space, and the product of the xi's is given a conserving metric, then the product includes various naturally occurring isomorphic copies of each coordinate space xi. So that's what's conserved is sort of like the projections onto the factor spaces preserves sort of the metrics on those, or conserves, I guess, the metric on those. Theorem 164, suppose n in n, and for each I in n sub n, xi tau I is a non-empty metric space. Let E be a conserving metric on the product space. For each j in n sub n and a in p, let xj comma a equal the space where you have all points of the product space where xi is ai for all I, not j. Then the map x to xj is an isometry from xja onto xj. So here's my proof. Let J and N sub N and A and P and phi of J of X be the projection function onto the jth coordinate space for X and P. Since XJ is not empty, phi of um, that the point here for X and uh, with coordinates A1, A2, to XJ, comma, all the way up to AN is equal to XJ. That's what the function does. It's the projection onto the coordinate space. And phi j x equals phi j y, then xj equals yj implies x equals y for all. In other words, it's injective. Um, uh, where did I prove? So I said phi j is a bijection. Did I show that it's onto? Oh, here. Sorry, this is this shows that it's onto, and then this part here shows that it is injective or one-to-one. Okay, so that means that phi j is a bijection. Lastly, for any yz in xj comma a, yi equals ai equals zi for all I not j, then tau j of yj comma zj is equal to the max of, we're just using the mu infinity definition, is less than or equal to EYZ, which is less than or equal to, um, again, I'm just using mu1 here, right? That both of those things just simplify to give you tau j of yj zj, since tau I of yizi is 0 for all I not j. Um, Implies E of yz equals tau j yj comma zj equals tau j of phi of y comma phi of z. So that means that phi is an isometry from xj comma a comma e to xj tau j. Some of these things are hard to actually just read out just because of there's so many subscripts and everything. But hopefully it's not difficult to follow. Like I said, if you want to, you can download this for free from the Patreon page if you want to read it in more detail. Example 1.6.5. Here they're giving us an example. R1, R1 comma the three tuple 0, 0, 0, which is the set of all A and R3 where A2 equals is equal to the set of all A and R3 where A2 equals A3 equals 0. In other words, that's the x-axis. In R3 is isometric to R. In fact, more can be said. In fact, any line in R3 is isometric to R because for AB in R3 with B not 0, the map T to A plus TB over delta sub 0 of B is an isometry from R to the line A plus TB for T in R. Uh, okay, and then I just have to move over to the last section here in the second set of lecture notes here. So this is the last section, which is kind of short. So we're almost done with the summary for chapter 1. This is section 1.7, metrics and norms on linear spaces. All right, an arbitrary metric need not have the algebraic properties that we associate with familiar examples such as R, R2, or C. When we define a metric on an arbitrary linear space, we require that the metric interact with its algebraic operations. Suppose that V is a linear space over R or C. Linear space meaning a vector space, right, over the field R or C, real numbers or the complex numbers. We want to define a metric D on V that is determined by a length function called a norm, meaning that we should like for all A, B, and V, the length of the vector B minus A to be equal to the distance from the vector B minus A to 0, which should be equal to the distance from A to B. And 2, the length of lambda A should be equal to the distance from the vector lambda A to 0. Which should be equal to the absolute value of lambda times the distance from A to 0 for any scalar lambda. All right, here's our first definition in the section 1.7.1. Suppose V is a linear space over R or C. Suppose the notation B dot 20.3 just means it's referring to appendix B, which I think he has an appendix on set theory, I think. Suppose that this function, which we denote by these double bars, is a real function defined on V such that for each x, y, and v, and each scalar lambda, each scalar alpha, we have that. Well, I'll just call it the norm because that's what it is. The norm of x greater than or equal to 0 with equality if and only if x equals 0, and the norm of alpha x equals the absolute value of alpha or the modulus of alpha, depending on whether it's a real or a complex vector space, times the norm of x. And also the triangle inequality holds, which says that the norm of x plus y is less than or equal to the norm of x plus the norm of y. Then we call this function a norm on V, and V equipped with this norm is called a normed linear space. Okay, the norm of X is called the length of X with respect to that norm. If W is a linear space of V, comma, with the norm, then W with that same norm is also a normed linear space, and is called the normed linear subspace of V. So we're thinking of W as a subspace of the vector space V with the same norm. All right, here's the theorem, 172. Suppose V is a normed linear space of the function D defined on V times V by taking the ordered pair AB to the norm of A minus B as a metric on V. And here's the proof. Again, I won't belabor this. You just show that it satisfies the three properties of being a metric. So you can pause that if you want to see it. Definition 1.7.3, given a normed linear space V, the metric 172 is called the metric determined by the norm. We shall always regard a given normed linear space as a metric space with the metric determined by the norm. So we'll just assume that, unless stated otherwise. Example 174, the absolute value on R and the modulus function on C are the prototypes for norms. They determine the Euclidean metrics of 113 and 115 respectively. The Euclidean metric on Rn is given by that function, which you should be familiar with. For each p in the interval from 1 to infinity, where we include 1, the function, which is called the p-norm, given by that sum, is a norm on Rn, but this will not be proved until later in chapter 12. Right, example 175, the metric that takes AB to the sum of the absolute values of the differences between the coordinates on R2 mentioned in 1113 is determined by the norm that takes X to the absolute value X1 plus the absolute value X2. More generally, if P equals 1 in the example 174 that we just looked at a second ago, for each n and n, the function X to the sum of the coordinates of X, the absolute value of the coordinates of X is the norm, uh, the p norm, but where p is 1, in other words. The proof of this is much easier for p in the interval from 1 to infinity. So I guess we'll prove that in question 124 in the exercise set. All right, example 176, suppose n is a natural number. The norms, the p norm where p is 1 or 2, are the norms that determine the metrics mu1 and mu2 respectively. And the norm where uh, you know, uh, I don't know how to say this, but the norm with the subscript infinity is the max, or I guess it's called the infinity norm, but we haven't really talked about the terminology here, but is the max of the absolute value of the coordinates for all I in n sub n determines the metric mu infinity on Rn. And again, we'll prove that in the exercise set. He says, see question 124. Example 177, we can define norms on linear spaces over Q by restricting the norms of real and complex vector spaces to Q. Also, the p-adic norm is another norm on Q. Example 178, suppose V is a linear space. Suppose D is a metric on V that respects the algebraic operations on V in the way discussed at the beginning of the section. Then D is a metric determined by a norm. And here we show that. So consider the point function D delta sub 0 on V. For all x, y, and v and the scalar alpha, we have delta sub 0 of x equals dx comma 0, which is greater than or equal to 0 with equality if and only if x equals 0. Delta sub 0 of alpha x is equal to d of alpha x comma 0, which is the absolute value of alpha times d of x comma 0, which is the absolute value of alpha times delta sub 0 of x. And also triangle inequality follows here. So delta sub 0 is a norm on V, and D is a metric determined by delta 0. So yeah, we're almost at the end here. Example 179, linear spaces that admit metrics that are not determined by norms. For example, let V be a non-trivial normed vector space, meaning V is not, just the vector space containing the zero vector. With metric D determined by the norm, let V be a vector in V, where V is not zero, then at least one of dv0 or d 2v comma 0 is neither 0 nor 1, since the norm of V is not 0, so D is not the discrete metric, for example, on V. All right, so you could have, metrics that are not given by a norm. Question 170, 1710, this is the last thing that I'll do for this video. Every set can be endowed with a metric. Can any linear space be endowed with a norm? So here's an interesting question. And it turns out that you can, under certain caveats. You have to, in order for this to be true, you have to accept the axiom of choice, or Zorn's lemma, if you prefer that formulation, because existence of a basis implies existence of a norm, and you need the axiom of choice to guarantee an existence of a basis. For example, let V be a linear space with basis S, then the minimality of Z as a spanning set ensures each V in V has representation, so given by this linear combination of the basis vectors, where only a finite number of the lambda Vs are non-zero, and the representation of V as a linear combination of elements of S is unique. So we can set the norm of V to be the maximum of the coefficients of the the absolute value of the combination. Sorry, we could set the norm of V to be equal to the maximum of the set of the absolute values of the coefficients of the linear combination of the S's. Using the triangle inequality for the modulus function, it's easy to show that this is a norm on V. Okay, and that's the summary for chapter 1. Kind of long, but like I said, let me just stop my screen share. If you want to go over any of this in detail, you can download my summary for chapter 1 on the Patreon page. Let me know what you think down below. I'll be doing the problem set at some point soon on the channel, and I did want to read out the author's sort of preface to you guys, but I'll do that in another video because I have a bunch of other things for work that I got to get done today. So I'll see you then, and like I said, let me know. I'd like to hear from you down below. It's been a while since I posted a video. See you guys in the next one.